Hello, my name is Jared Martin. This is my presentation for Lab 1 for the ASE 3813 Intro to Orbital Mechanics final project. Lab 1 is about CubeSat, a proposed CubeSat mission to observe a list of recently active volcanoes in the United States. In Lab 1, we must design a circular and an elliptical orbit in order to determine the best orbit for CubeSat with the constraints of orbits between 250 and 550 kilometers. We must then compare the orbits over a 2-week window from January 1st, 2024 to January 15th, 2024 in order to find the most optimal orbit. Finally, we must determine from a list of 3 which rideshare launch providers can provide an orbit closest to our optimal orbit. In this lab, I will use STK12 and MATLAB in order to run these calculations to find the optimal orbit, a realistic orbit from a corresponding capable launch provider, and additional orbital information. For our first piece of data, deliverable 1, we will be conducting each calculation using the J2 perturbation propagator. Here's a list of the 6 orbital elements, of which we will be using 4. Also listed are some useful equations which were calculated by hand in order to find certain required data throughout the lab. We will be taking into consideration the semi-major axis, inclination, eccentricity, and argument of perigee, while leaving right-hand ascension of the ascending node, or RAN, and true anomaly alone for future lab research. Also listed here are the 10 recently active volcanoes which STK-SAT is supposed to scan. For deliverable 2, we are testing a circular orbit for STK-SAT. With the provided MATLAB code, it was determined that the optimal circular orbit was provided by a semi-major axis of 6,928 kilometers with an inclination of 56 degrees at an eccentricity of 0, which provides our circular orbit, an argument of perigee of 0 degrees, RAN of 0 degrees, and a true anomaly of 0. This orbit allowed STK-SAT a total observation time of 5.23 hours. Figure 1 provided below is a plot of the circular orbit as it corresponds to mission altitude as well as STK-SAT's inclination. For deliverable 3, we are testing an elliptical orbit for STK-SAT. With the provided MATLAB code, it was determined that the optimal elliptical orbit was provided by a semi-major axis of 6,778 kilometers, which was found using the semi-major axis equation listed in the equation slide. With an inclination of 56 degrees at an eccentricity of 0.0221, an argument of perigee of 249 degrees, RAN of 0, and true anomaly of 0, this orbit allowed STK-SAT a total observation time of 5.33 hours. For deliverable 4, observation time, we can observe that an elliptical orbit provides a 1.855% increase in viewing time over the targets for our STK-SAT when compared to the circular orbit. For deliverable 5, I had to determine from a list of 3 which rideshare provider could provide the best launch profile for our STK-SAT mission. Through using the MATLAB code, I was able to determine that option 2, a rideshare on an orbital ATK launch to the ISS, would provide the most realistic launch profile with an observation time of 2.75 hours. It is assumed this launch will be on an Antares launch vehicle with a Cygnus upper stage, since Orbital ATK uses this launch vehicle for missions to the ISS. Thoughts and future optimization, other launch providers. To further optimize our results, we could study other launch providers to see if there's a better rideshare option available to launch our STK-SAT into an optimal orbit. Information on launch capabilities come from information on allrockets.space, which includes launch information links for each company and their respective rockets. Listed below are a few launch providers and their launch vehicles which could be examined for feasibility for our STK-SAT mission. The rockets shown here are approximately to scale. This lab could easily be modified to examine other launch vehicles with the provided manufacturer performance information. These launch providers and launch vehicles include, but are not limited to, Rocket Lab and their Electron rocket, which has been optimized for small satellite payloads, Northrop Grumman's Pegasus XL rocket, which is launched from below a jet aircraft, Northrop Grumman's Minotaur 4 with its solid rocket booster first stage, the Arianespace Vega rocket, which is made for small payloads, and even the Ariane 5. To demonstrate this further research, I will test the feasibility of using a rideshare option on a Rocket Lab Electron launch. While their website lists 2 launch complexes as available, I will model a launch from Launch Complex 1 on the Mahia Peninsula in New Zealand. This site can support launches between 39 and 120 degrees of inclination, which covers our 56-degree optimal inclination. Using a chart provided from Rocket Lab and information from their technical sheets, we can determine that Electron is capable of launching a 240-kilogram payload in a 56-degree inclination circular orbit of 500 kilometers. With this information, we can determine that a rideshare on Electron would provide STK-SAT with a 4.69-hour observation time. If an Electron launch were to take place near our desired orbit, it would provide a greater observation time than the Orbital ATK rideshare from Deliverable 5. In this scenario, the only limiting factors are launch availability within range of the Electron's second stage, as well as weight restrictions for said launch profile. While Electron is one of the smallest launch vehicles in use, it is designed with CubeSats in mind. This does not mean that all of the larger rockets could provide a better rideshare option, because many factors such as launch site availability and inclination offsets for the primary payload will greatly impact a launch provider's capabilities. Rocket Lab set out to design an effective small satellite rideshare option, and as we see with the mission projection above, they have accomplished just that. With this, we can conclude that Electron would be a better choice of rideshare option, providing a rideshare mission is available with similar mission parameters as our STK-SAT. Thank you for watching my presentation. All information not provided for this project is listed below, including links for anyone who is interested. May your launches be successful and your orbits be optimal.